Hey there! In this video we are going to look at one of the most practical applications of derivatives, and that is optimization problems. Or in other words, problems where you need to find the maximum or minimum value of some quantity in a situation. Engineers, scientists, designers, economists, and others need to solve these kind of problems all the time, where they are looking for the biggest or smallest or fastest or most efficient solution. We will look at a number of different problems in a variety of situations and see how calculus can be used to solve them. All right, we're going to look at 5 different examples, and they're all going to involve different contexts and different mathematical relationships, but there's going to be one thing in common to all of them, and that is our strategy for solving them. The very first step or thing that you have to do that I think some people skip over when they're trying to solve mathematical problems is just taking time to understand the situation and the problem. A lot of times people want to right away write equations and start doing the mathematics. Part of it is understanding what's going on in the relationship, so that is important. The second thing then in our approach is going to be to identify variables, quantities involved, and any constraints, and look for equations that we can write. After we've done that, we are going to look to use the different equations and constraints to try and eliminate variables as necessary to produce a function of one variable that we can use, and then we're going to optimize that function, find the maximum or minimum in the situation. After that, if you're to the point where you're pretty good with a lot of the calculus we've done, it might be a little bit of sort of autopilot after that, because it's going to be just using calculus to find critical points, using the derivative, and then using that to find maximums and minimums. And then last is taking our results and interpreting them in the context of the situation, the problem, and then lastly, thinking about endpoints, because critical points are going to lead to some interior maximums and minimums, but sometimes the endpoints are actually the maximums and minimums. So that's something we need to think about. All right, let's tackle the first example. Our first example isn't going to be a truly real-world contextual example, but we're going to use this to try and nail down our method and see what the approach is going to be. So in this problem, we have that the sum of two non-negative numbers is 20, and we are looking for those numbers so that the product is, in part A here, as large as possible. And so, as I said before, the first step is just understanding the situation. The situation is not necessarily all that hard to understand, but I know that maybe in the past you zero into the numbers in a problem, but some of the words are going to be important too, right? First of all, we have sum here. We have the fact that there are two numbers. They're non-negative, and they do have a sum of 20, and then we're talking about the product being as large as possible. All those things are important, and we'll try and quantify that right now. If you wanted to, you could start to just think about the numbers and say, hey, sum of two numbers is 20. Well, what could they be? They could be 10 and 10, they could be 11 and 9, they could be 20 and 0, lots of different things. You could make a list in your mind, and that's not a bad thing. You might even come up with the idea that thinking, hey, I think I've got the answer to this. That doesn't mean necessarily we're not going to go through and do all the calculus. We're starting with simple problems here to get the method down, but then you're going to be able to move on to more complicated things that aren't necessarily so obvious as to what the solution is. So, first step after we understand what we're looking at here is to identify some variables. And as said, there are two numbers, so what I'm going to do is just call those x and y. X and y are going to be the numbers. And it does talk about the product being as large as possible, so I am going to use P for product. It also talks about the sum, but that's not a variable in the situation because it says the sum is 20, so we don't need a variable for that. So the three variables we've got there, x, y, and p, are enough. And then we're going to try and quantify the relationships and constraints in the problem. So it talks about the product, and so we're going to write an equation for product. You need to know that product means the result when you multiply numbers. And so we're just going to write that p is equal to x times y. Now, there is one other equation we can write, and this one is going to be what's described in the first sentence here. The sum of them is 20. And the way you can write that, of course, is you can just write that x plus y is 20. Now, that equation right there is going to be called our constraint. The fact that the sum is 20 is going to be called the constraint, and that is what we're going to use, that equation, to eliminate some of the variables, one of the variables in this case. We have three variables here, and we need to produce a function that is one quantity as a function of another quantity. So if we rearrange this equation, we can turn it into y is 20 minus x, and then we can use that to replace the y in this equation and make this x times 20 minus x, because y is 20 minus x, and so we change the y to 20 minus x there. And I am going to start calling this now p of x, just to emphasize now I've turned it into a function of one variable. I have the product as a function of x with this equation. You don't need to do that. You could still just keep calling it p if you prefer. Up to you. I like to do that just to emphasize that. All right, and you can, of course, expand this, and what you're going to get then is that p of x is equal to 20x minus x squared. And that is the function that we are going to optimize. Look for, first of all, here the maximum value, the product being as large as possible. And the way we're going to do that is we are going to look first for some critical points, which is, of course, where the derivative is 0 or undefined. And so to do that, we need to write what the derivative is. And the derivative, p prime of x, is going to be equal to 20 minus 2x. Now, we can think about 0 or undefined. Well, this is just a linear function. If it's any kind of polynomial, it's never undefined, so we don't need to worry about that. And we're just going to look where it's 0. So what you can do then is replace p of x with 0 there. And then, of course, that's equal to 20 minus 2x. We can solve that equation. That equation, if we move the 2x to the other side here, it's going to be 2x equals 20. And then, of course, x is equal to 10. So that's our first value for x. What we can do with that then is we can find what the y value is, because we had our constraint up here that y is 20 minus x, that the two of them add to 20. So we can just say that y is going to be equal to 20 minus 10. And then that's, of course, 10 as well. So we've got that the two numbers are 10 and 10. And then we can work out the product. Either I can go to the original equation, x times y, or I could actually go back to this and just use the x value if I wanted the product. Either one. You can go to the original equation you started with or to that function that we produced, and either one would work. I'm going to do this because I have the two values here, and that's what I'm asked to find. So product is then 10 times 10, which is, of course, 100. And then really what we should do now is we should confirm that that is indeed a maximum. When you're solving these problems, you're going to find that often the value that comes up, if you find one critical point, is the one you're looking for. Unless you've set it up incorrectly, it's going to be the one you're looking for, and it's indeed, if you're looking for a maximum, it's going to be a maximum. But if you want to, the way you could confirm that, the fact that the product is 100 when x is 10, that it is indeed a maximum, is you could use the first derivative test that you've used before, right? You could check a point on either side of x is 10 in the derivative, right? You could check to the left of 10. You could put a 9 in here. 20 times 2 times 9 is a positive number. So you know it's going up on that side of 10, and then you could put a number on the right side of 10, 11, right? If you put 11 in there, you get a negative number. So downhill, so you know it changes from up to down, the derivative, so it is indeed maximum. Or the other way is you could just check the values on either side. So you could think if the numbers here are 10 and 10, that gives me 100. And if you made the numbers instead 9 and 11, if you made x go down 1. 9 and 11 multiplied to 99, which is less than this. So that's going to tell you it's lower on the left. And then you could check a number bigger, right? You can make x 11, that would be 9, and that's also 99, so you know it's lower than that, so you know that that's a maximum because the values of the function on either side are lower. So either way, so we can say that the product is as large as possible, and that product being 100 when the numbers are 10 and 10. That's the answer, the solution to our first part of the problem. All right? Now the second part, part B, what if the product we were looking for was as small as possible? What would that be? Now, we didn't have any other critical points, so what do we need to do here? What we need to do is we need to check if there are any endpoints in our situation. And in this situation, there are. And what it has to do with is thinking of the domain of the situation that we're talking about here. It did mention that the numbers have to be non-negative. So for us, the domain for our x value means x has to be greater than or equal to 0 here. And that means that in our situation, y has to be greater than or equal to 0. Both values have to be not negative, so positive or 0. And if we combine that with the fact that they add to 20, it means that each of them is greater than or equal to 0 and less than or equal to 20, right? They can't be more than 20, because if one was more than 20, the other one would have to be negative, all right? So x has to be between 0 and 20, and y has to be between 0 and 20. And so what that means, our endpoints are going to be, one endpoint is going to be our left endpoint for our function here, is if x is 0. And then the other point is if x is at its maximum, it's 20. So if x is 0, y is 20. If x is 20, y is 0. And both of those situations mean that the product is going to be 0. If one of the numbers is 0, of course, the product's 0. So that's going to be our minimum in our situation is at the endpoints. So the product is as small as possible, 0, when the numbers are 0 and 20. We don't have to say both of these. These aren't actually two different solutions because we introduced the x and the y, but when we're talking about two numbers, we're just saying they're 0 and 20. That's when it's the minimum. All right? Before we look at another example, we're going to have a quick look at this graphically, both to confirm what we did here analytically and to try and make a few connections between the two representations to really understand what's going on. All right, so what we can do is we can put our function in here. P of x equals 20x minus x squared. Now you notice that that doesn't look like anything that has a maximum, but of course we have to get the dimensions right here. So what I would suggest doing is squish this down a bit till it starts to look like something you might recognize more. And then this side here. So that's our function, which we expect it's a quadratic, right, with a maximum there, and that's the value that we found. When x was 10, the product is 100, right, because this graph shows the product as a function of x. If we were really doing this properly, what we would do is we would put a restriction on this function. So we would do that, and we would say 0. We'd go down in here into this menu and we'd say that, and we'd say x, we'd put another one of those, and we'd put 20, and we'd put a colon there. And that gives us our graph. Get rid of that keyboard. All right, so that's the actual function because we don't want negatives there, right? That's why we had this maximum here, and we had these endpoints that were our minimum there and there, all right? Without this, if we hadn't had the non-negative thing, right, if we had just gone like that, without this, there wouldn't be a minimum because you could keep going along here, and it's not going to let me go to nice integer values, but you could get 21, which would make the product, right, the numbers would be 21 and -1, so the product would be -21. You could go to 22 and -2. It's not going to really let me stop there nicely either. Maybe, there we go. 22 and -2, right, the numbers gives you negative 44. So that would just keep going down. And the same with the other way, right? You get the same thing. So there'd be no minimum if it wasn't for that restriction that they have to be non-negative. All right, let's look at another example. In our next example, we have a situation where we have a farmer who wants to fence off a rectangular enclosure along a straight river. And the key here is that the river is going to form one of the sides, and so it doesn't require any fencing. If the farmer has 200 meters of fencing, what are the dimensions of the enclosure that have the largest area? Now, again, we often in math problems zero in on the numbers involved, but there's other things that are important here. It is a rectangular enclosure, and we have this straight river that's going to form one of the sides, so it doesn't require any fencing. And then we're looking for what dimensions are going to give us the largest area. So this is a situation where a diagram would be an excellent thing to do to start. So you can draw a river and then draw this rectangular enclosure there. And we do not have a side along the river. I guess the farmer's cows are smart enough not to walk in and drown themselves. So we need these three sides. And so we have those lengths. This is a length of fencing, and it sounds like it's in total to be used for those three sides. And so we can start to quantify this and introduce some variables. You could again just use x and y, call the two dimensions x and y, but I think it helps to be as specific as you can. So I'm actually going to call these ones d, and I'm going to call that one w. And the reason is because I'm going to call that one d because I'm going to say it's the distance perpendicular to the river, just to be specific about it, that distance. And then I'm going to use w as the width, and we can say parallel to the river. And then we're talking about maximizing the area, so we're going to use A for area that is enclosed. All right, and then we can start to write some equations here. I'm sure you know the area is going to be just those two dimensions multiplied d times w. And then we also have this constraint. The constraint is going to be the perimeter of the thing constrains what we can do. So we're going to say that our constraint here is that we have two d's, right? We need to create two of those sides plus one w across there, and that has to all add up to 200. So that equation is our constraint. And what we're going to do then is we're going to use that equation to eliminate a variable. And to do that, we want to isolate something on this side here. So I'm going to choose to move that 2d over to the other side and make it into w equals 200 minus 2d. I prefer that because otherwise if you try to isolate the d, you got to divide by 2 and it gets a bit yucky. So we don't want, not that having fractions involved is maybe I shouldn't use that word, but it's easier if we can keep those things out of it here. And so if we take this equation now and we replace the w with what we know it's equal to, w is equal to 200 minus d, we can say that that is going to be equal to d times 200 minus d because that's what w is equal to. Replace w with that. All right, and then I'm going to call that a of d. I'm going to start to use function notation again because now we have it as a function of one variable, area as a function of that distance from the river. And so we can again expand that. So we can say a of d is 200d minus 2d squared. And then we're going to go about finding the maximum that we are asked to find. And we're going to do that by using the derivative. And so we got to find the derivative first and then look for critical points. So a prime of d is going to be equal to 200 minus 4d. And then to find critical points, I guess again we should recognize this is not undefined ever, so we're only worried about where the derivative is 0. So we're going to put a 0 there and then solve that equation. If 200 minus 4d is 0, again, I'm going to move that to the other side and make it 4d is equal to 200. And so if we divide by 4, we've got d is equal to 50. And then we can now find the w value. Again, you can go back to this constraint here and substitute it in. So if I substitute in, I'm going to have w is equal to 200 minus 2 times 50, right? Just replace that d value with what we just found of 50. And then, of course, that's going to be w is 100. Then we can find our area. So we're going to go up over here. Our area is going to be equal to d times w, right? You can go back to this again, or you could go back to this if you wanted to. I'm going to go back to my original d times w to find my area. And so 50 times 100 is going to give me 5,000 square meters, right? The units should work out. If you're multiplying meters times meters, you're going to get meters squared, which is area, what we want. You can go and confirm that that's a maximum if you want, and you can do it again 2 ways. Use the first derivative test, right? Substitute values on either side of d being 50 into our derivative. On one side, you're going to get that it's positive, derivative positive, and then on the right side you're going to get that it's negative. I'll leave that to you to do if you want. Or you can check values around it, right? You could make this down to 49, in which case if d is 49, then w is going to end up being 102. You'll find that that's a lower number than that. And if you go to the other side, d is 51, well then w is going to end up being 98, and you're going to find that that's also a lower number, so that confirms that that's a maximum. But as I said, when you do these problems, often if there's one critical point you find, it's going to be the solution, and it's going to be what you're looking for if you're looking for a maximum. All right, so then we can go ahead and write our solution. We can say that the dimensions of 50 by 100 are going to give us the maximum area. The problem didn't actually ask for the maximum area. It just asked for the dimensions if you go back and look at that, right? So it just says what are the dimensions of the enclosure that has the largest area, but it doesn't actually say and tell us the largest area, but I think it's not a bad idea to put in there. So what I'm going to do is just put in brackets here 5,000 square meters. I actually should have maybe been a little bit more descriptive about this. I just said dimensions of 50 by 100, but I probably should have said 50 meters perpendicular to the river and 100 parallel to the river, just to be specific about that, right? And when you look back at the picture here. Maybe the other thing you might say is, you might say, hey, I kind of was expecting it to be a square, because it seems like a square should be the most efficient way to create the maximum area there. And if this was a perimeter we had to make into all 4 sides, if we had to have this side and there was no river there, the answer would have ended up being a square. But having this constraint of the river can be used as part of it, it ends up being a longer this way and shorter the other way, because you're making more use of the river then. The river side is longer, which is why it doesn't end up being a square there. All right, so now the last thing we'll say here is we don't need to consider endpoints here because we found our maximum. If you did want to think about the endpoints, right, the endpoints would both be a minimum, and that might be pretty obvious to you here. What it is, well, if you, well, I'll go back to the picture again here. If you decided you're going to take the entire 200 meters and just stretch it straight along the river there, where d is 0, then the width is going to be 200 along there. That would obviously be a minimum. It would be 0 square meters. And then the other side, the other way would be, well, if you just took the fence and went straight out and straight back, that would also be a area of 0, because d would be, you'd go 100 meters out, 100 meters back, and the width would be 0. So the endpoints, if you want to think about them, even though it's not going to lead to something we're asked for here, if d was 0, then the width would be 200, as I said, stretched out along the river. That wouldn't be very smart of the farmer to do, because then he's got no area for the cows or whoever's going in this enclosure. Or the other way, if you made the width 0 and d 100, then it's also 0. So both of those result in an area of 0. But we aren't asked for the minimum, so we're not going to worry about that. And before we look at another example, we'll have a quick look at this one graphically as well. All right, so graphing this one, we'll put our function in there. This was a of d, and that was equal to 200d minus 2d squared. All right, that doesn't look anything like what we expect. This is another quadratic function, and it's got a negative squared term here, so we expect it to be an upside down parabola, which makes sense because we found that maximum. So if we squish that down and I move this over here, kind of zoom a bit there so we can see more of it. That is that. All right. And again, for this one, we want those endpoints in there. We don't want it to continue into the negatives. We can't have negative dimensions. So the way you can do that on Desmos is, again, put these curly brackets in here. In this case, I'm using D, right? I'm going to put in here that D has to be, got to go back down into this menu here again, that, D, that, and we said that the biggest D could be was 100. And then if we put a colon in there, that gives us our function, all right? The area as a function of that perpendicular distance, and we found that when we made that 50, we had that the area was a maximum of 5,000, right? This is area, this is the D value. And then those endpoints where the minimums are, this one down here, right? Where if D was 0, right? If you just ran the fence straight along the river, the area would be 0. And then this was if you took it and ran it straight 100 meters away from the river and straight back to the river, the area is also 0 there, all right? Let's look at another example. In this third example, we're going to change things up a little bit. First of all, this is going to be something that has to do in more the business realm, a revenue for a concert hall. But also what this is we're going to use a mathematical model to represent something in the real world where the something may or may not behave exactly like the model. This is something that mathematicians do all the time, create a mathematical model for something and to make some predictions. And we'll talk more about that after, once we go through and see what's going on here and understand it a little more. All right, so the situation here is we have a concert hall and they currently sell tickets for $30 each. And at that price, they fill all 600 seats in the hall. And they've been doing some market research that shows that for every $2 increase in ticket price, 20 fewer people are going to buy tickets to any given show. And what they're wanting to know is they want to determine the ticket price that maximizes the total revenue. Revenue refers to the money you take in a business before you've subtracted anything for costs or whatever. It's just the money you get from customers. So it's just going to be the money that they get from selling these tickets. And then we're going to, once we've determined that, we're going to calculate how many tickets we can expect to sell and then what our expected total revenue is. All right. So there's lots going on in here. There's lots of numbers, right? Our previous couple of examples only really had one number involved in each one, but this has lots of things going on here. So it's going to seem maybe a little bit more overwhelming at the start, but we'll try and quantify what's going on here. There's lots of different approaches that we could take here, but the one I'm going to take is I am going to focus on what the people that run this concert hall have control over, and that's how much they increase the ticket price. It talks about $2 ticket price increases, and so I'm going to make X equal to the number of times they increase the price by $2. There's some other numbers that are obviously involved here too, and we're going to use variables for those as well. It talks about the ticket price, so I'm going to use P to be ticket price. It talks about number of tickets sold, so I'm going to use an N for number of tickets sold. And of course, the thing we're looking at maximizing here is revenue. So I'm going to use R for revenue. And then we can write some equations relating all this. There's a lot of variables there, but we're going to write equations that relate all of those things, and you'll see that it'll work out nicely here. So the first equation we're going to write is something that's pretty basic in economics that relates revenue to the price you're selling something and how many you sell. All right. If you sell a certain number of tickets, like currently we're selling 600 tickets, and you're selling them for a certain price, at this point $30 each, you just multiply those two things to get your revenue, right? At current, $30 times 600 would give you your total revenue of $18,000. And so our equation is going to be revenue is equal to the ticket price times the number of tickets that you sell. Now, the reason I chose this as my variable that I'm going to use is because I can write my constraints based on that. My first constraint, the price is constrained here. The price you get by saying it's currently 30, but I'm going to increase it by 2 times whatever the value of x is. If the value of x is 3, if I'm going to increase the price 3 times, x is 3, and it's 2 times that for how much I'm adding on, right? 2 times 3. So I'm going to say that this is 30 plus 2x. 2 times the number of times I increase that price is going to give me the price, 30 plus that. And then I can also relate the number of tickets sold to that as well. So I can say that n is going to be equal to currently 600, but every time I increase the price, 20 fewer people are going to buy. So it's actually going to be minus 20 times x. Every time I increase the price, that times 20 is how many fewer people are coming. So you actually have 2 constraints here, and we're going to use them both to eliminate some variables. And so I can write that this is equal to, instead of price, I'm going to put what that's equal to, 30 plus 2x. And then I'm going to replace the number of tickets sold with what it's equal to, 600 minus 20x. And so that's that. Replace it with that. And then that's our function. And there's one variable involved, and the one variable is the thing I said that they have control over, is how much they're increasing the price. I'm going to use r of x for that because now that it's a function, revenue as a function of number of price increases x. And then we can go about working to find that maximum. First, maybe we'll write this in expanded form there, multiply out those 2 binomials, and that's what you'll get. And then we can find the derivative of that. The derivative of that, r prime of x, is going to be equal to 18,000. Derivative of that disappears. We just have 600 from that middle term minus 80x. Derivative of minus 40x squared is minus 80x. And then we can look for critical points. Again, we should maybe think this is never undefined, so we're not going to worry about that. We're just going to look where it's 0, and it's going to be 0 when that's equal to 0. And I'll move the 80 over, like the previous examples, over to there. That's going to be equal to 600. Divide both sides by 80, we're going to get x is 7.5. All right? And then we can use that number to determine the other things. So we can go back to our couple of constraints here and find the values for those. So we can find the ticket price here, and it's just substituting the value we got here, 7.5, into our equation for price, and then that's going to be equal to $45 for each ticket. And we can also find the number of tickets we can expect to sell as well by substituting 7.5 into that equation. So when you do that, you get that that is equal to 450 tickets. And then we can take those 2 things and we can work out our revenue. So our revenue is going to be equal to $45 per ticket times 450 tickets, which dollars per ticket times tickets is going to give us our $20,250 of revenue is what that is equal to. All right. You can go through and confirm that it's a maximum the way you did before. And so we can write our solution to the problem as being this model predicts that if we sell the tickets at $45, we can expect that it will result in 450 tickets being sold, and then that's going to give us the maximum revenue of $20,250. All right. In part B here, we're looking at, is there a ticket price that would give the minimum total revenue? And we'll have to do a bit of explaining with this and thinking about it. The answer is going to be yes, there is. Maybe intuitively you're already thinking about, of course there is. If you didn't charge any money at all, if you set the price at 0, you'd have 0 revenue, and you are correct. There's also going to be a ticket price that's so high that you're going to make no revenue as well. And so if we think mathematically about this, according to our model, we only found one critical point. There was no other critical point. So again, like the previous examples, we need to think about our endpoints for a minimum here. Now, if we were saying the price was 0, then we'd actually have x being a negative number because we'd be decreasing the price, not increasing the price. But in this situation, we don't really want to think about negative x values because in this situation, they are already selling all 600 tickets. So there's no reason they would reduce the price unless they were doing some charitable thing or something. But we're going to just think about this as that there's no need to lower the price. So we're going to keep x as greater than or equal to 0. We're not going to think about negative x values here. All right, so that's one endpoint here. X is going to be greater than or equal to 0. And for our other endpoint, we're going to think about something else here that once you think about it is fairly obvious, is you can't sell a negative number of tickets. And so what that means is n, our variable n, has to be greater than or equal to 0. So if we say n is greater than or equal to 0, and then we replace this with how it's related to x, 600 minus 2x, that has to be greater than or equal to 0. And so 600 has to be greater than or equal to 20x, which means x is less than or equal to 30. So if we combine those two things together, we've got x is greater than or equal to 0 and x is less than or equal to 30. So those are the two boundaries on the values of x here. All right. So if we think about those two things, if x is equal to 0, our left endpoint, if you will, then our revenue is going to be equal to 30, right? Because x equals 0 means we don't change the price, times 600, which gives us a revenue of $18,000. And then on the other side, the right endpoint here of this model, if x is 30, we're going to have to work a few things out here. We need to figure out our price if x is 30. So price when x is 30 is 30 plus 2 times 30, right? Because we've got our base price of 30 and x is 30 we put in there. And so that works out to 90, ticket price of 90. And at that ticket price, we saw before that that's going to give us, if we substitute 30 in there, 600 minus 2 times 30 is no tickets sold at all. And so our revenue there is going to be 90 times 0, which is, of course, $0 revenue, right? So according to this model, if we raise the price that much, no one's coming to the show, right? So we can write that down here and we'll think about it a little bit more when we look at this graphically. So we can say that this model predicts that setting the ticket price at $90 will result in no tickets sold, and then the minimum revenue is 0. All right. Let's look at a graph and we can think a little bit more about this. All right, so graphically, here is our revenue function. This one, I've got it punched in already so that we don't have to take time to do that. Set our graph up. Remember that our revenues were going up pretty high, up to 18,000. So there's that. Move it over there. And it's what you expect, that it's an upside down parabola. Again, that shape. And maybe we'll do that. And as we said, we looked at endpoints of this, so that's without any endpoints, but of course this, we can't go into the negative number of tickets sold, so we definitely need a right endpoint. And you could argue whether you think x could be negative or not. If we go with what I had before, then that's what it's going to look like, that portion of the curve like that. If you thought that x could be negative, you could have this other part of this all the way down to there. But in any case, it can't go into the negatives there according to this model. Now you might say that this model, like 30 price increases, so a ticket price of $90, there may still be people who are going to the show at that. So it's only as good as the model is, right? And this model we have is fairly simple, right? And realistically, maybe what it has in reality, this is a more complex thing that I put in here. Maybe it doesn't go straight down to 0 here and suddenly there's no people buying tickets. Maybe it's more like it sort of trails off like this as you go to the right. Maybe there's always someone who's going to buy tickets to the show, like it's decreasing, but maybe it's always something that someone has money they want to spend on this. So That's obviously a topic for something else where we can look at more complex models of things. All right? Well, this video is getting pretty long here, and we've only done 3 examples so far. They do take time to understand and think through and solve. There are still 2 more to do, but what we're going to do is those are going to be in another video, part 2 of this. The link's up above here. Have a look at that, and we'll see you there.